Now that we have developed all this framework for analyzing music as a complex system represented by a network, and even how we can use this representation in a computational settings, we can add let's say the last step in this development, that is to use this representation, these graphs, these networks, to extract quantitative information on the complexity of music. So the question of complexity, of measuring complexity of something like music is in a way not particularly well defined, and what it means complexity. Complexity in this context wouldn't mean if a music is more complicated than another one. There might be music that we perceive as simple that are indeed very complex in terms of a measurement of complexity based on the topology of the underlying network. A central concept in this is evaluation or quantification of amount of information that a network kind of represents, and a way of measuring complexity in a more kind of scientific mathematical sense is to use concepts like entropy, for instance, and how we can extract from a complex network representation quantitative information about what we would call a measurement of complexity. So in particular, entropy is a very good measure for this kind of analysis, because is characterized by network properties, so we can extract directly from the network properties, like the degree distribution, for instance, or the analysis of the paths that we need to follow in order to go from one node to another, and link this to some sort of abstraction of a measure of complexity. Eventually, we would like to talk about scaling invariances and universality classes that are concepts that we mediate from the statistical mechanics of networks. Although we still have to keep in mind that our musical networks are relatively small, and so extracting or extrapolating too much from these dimensions might not lead to meaningful results. In work that we have been doing, myself and my collaborators, in the past years, we looked at quantifications of concepts like entropy and information, and we used basically three different approaches in order to verify that indeed the results that we were obtaining were not influenced by the technique itself, but they were actually a representation of something that is deeper and lies into the structure of these networks. So we used what is called the Kullback-Leibler divergence. That is basically a measure, in layman terms, a measure of how much a particular network diverges, or a particular structure system diverges from an average of many of these systems, many networks, for instance. Mathematically speaking, has to do with evaluating quantities that are based on a mathematical representation of the network in terms of what is called the conditional degree matrix. And you'll find references in the website for all the papers that you can read about these concepts. Another technique that we have used to quantify complexity is called diffusion entropy analysis, that rather than being based on the network itself or its topology, uses a time series analysis. So in a way mirrors what we have done in the definition of our score networks as a network on one side and kind of a dynamical time series on the other. And finally, we also looked at a different set of data, and I'll talk about it in a little bit, to evaluate what is called the computable information density. That is basically a measure of order of a data set based on its data compression quality. So basically, it's an evolution of what is commonly known as the Kolmogorov complexity that gives us a measure of information content based on how much we can compress that particular system in computational terms, like when you do a zip file, for instance, and use that as a measurement of information density. Here I'm showing you a result that we obtained using a variety of data, score data of many different composers across centuries. So we start from Josquin-des-Prez in the second half of the 15th century, and we end here with Gustav Mahler, end of the 19th century, beginning of the 20th. And we are here showing a parameter that is extracted from this diffusion entropy analysis that I was discussing earlier. And as you see, although the data are very scattered, the average behavior shows an increase of harmonic complexity, in this case, from, say, the Renaissance to the modern era. That means that these kind of measurements capture something that is indeed known from a musicological and historical point of view of music, but it quantifies in a way that is very independent of any prior knowledge. It is based just on the structure and topology of the networks that are obtained from the corpora of the different composers. As a comparison here, I did the same kind of analysis for more recent and popular songs, and you see here something goes from Michael Jackson and the Queens and Madonna to Frank Zappa, and I would say that it's not surprising, for me at least, that Frank Zappa complexity is higher than many other well-known example here in this graph. Now we turn to the Kullback-Leibler divergence, and here we see exactly the same sequence of composer that we had before. Now the behavior of this data, this curve of this measurement is opposite to what we saw in diffusion entropy analysis, but this is consistent with the definition of this KL divergence. We expect the KL divergence to be decrease for increasing complexity, and so the data here are completely correlated in this respect with the previous one that used a completely different measure. So it seems that different technique give us the same result, at least qualitatively, in terms of the measurement of complexity of harmonic structure in the history of the last 500 years of Western classical music. Both the Kullback-Leibler and diffusion entropy analysis are run on the network models from a corpus of compositions. And as I mentioned many times, we are limited in the number of data that we have, not just that the networks are small, but also the number of networks that we have, the number of scores, are not in large numbers. And I mean, this is also part of the fact that a composer can write up to a given number of pieces in his or her life. So in a way, our data are limited, and we want to kind of expand and test this idea of increasing complexity using different data sets, and for that we turn to Spotify. So Spotify, that all of you probably know very well and use, is a web service of music streaming that has an enormous collection of tracks and composition then, that provides developers and researchers and scientists with a web API that we can use to interrogate part of this database. We don't have access to full tracks in the web API, but we have access to a lot of metadata and some quantitative information that can be useful in order to verify our predictions. In particular, in the data repository that Spotify opens to the developer community, there are tools for the analysis of the audio in each track. And in particular, one of these quantities that is provided in the database is called the chroma vector. The chroma vector is, in a way, the parallel of our slicing of the chords, so our node structure, the vector of pitches, in the audio realm. Basically, what you are doing, you are analyzing very short segments of the audio, doing Fourier transforms, and extract the most relevant frequencies in the spectrum that correspond to the individual pitches in the track, in the sound sample, and map this onto a vector that is 12 units long, so it maps the equal temperament of the 12 chromatic pitches of the chromatic scale, and can be used exactly in the same way as we used the score network. So we could use it to build a network itself, or we can use it in this particular case to evaluate the complexity of the information via the compression algorithms. So here is again the similar plot to what I showed you before, where now we use the computable information density as our measure of complexity. And again, we can see if we look at the evolution in the centuries from the Renaissance to the modern era, we see a similar behavior to what we saw before using the KL divergence or the diffusion entropy analysis. What is very interesting here is that we are using a large corpus of recordings. So there are this information not only contains a kind of a score aspect, the composition that is the same, but also a performance aspect that is performed by different groups, by different ensembles, potentially different instruments, instrumentations, orchestration, and so on. So it gives us a very broad picture of how we can quantify complexity in this particular aspect. The last thing I want to make you notice, and this is more for some of you that might know more of the history of music in the 20th century, the last three data points in this graph correspond to the composer Arnold Schoenberg, who's the father of atonal music in a way, and that here is represented by two data points or two distributions, because there is a change in his aesthetics around 1913, 1915, where he goes from a classical harmonic language to a more atonal language, and this corresponds to different level of complexity that are actually well represented here in this data.